Let's jump right into this explainer of the AISC 360-16. We're looking at the ultimate rulebook today, folks. It's literally the unseen structural DNA of our modern world. When you look at a skyline, sure, you're seeing architecture, but beneath all that glass and concrete, there's a highly engineered framework, and it's governed by the exact specifications we're going to unpack today. Seriously, have you ever wondered what keeps a 50-story steel skyscraper from just collapsing? It's really easy to take for granted, but day in and day out, buildings are constantly under attack. We're talking about the relentless forces of nature. Gravity constantly pulling downward, gale force winds pushing laterally, and, of course, the extreme, unpredictable threat of fire. Think of these forces as the antagonists of our story. And this specification, the AISC 360-16, well, that's the structural engineer's definitive toolkit to defeat them. To guide us through this, we've broken our explainer down into 5 key areas. 1. The Steel Construction Rulebook. 2. Consensus and Continued Evolution. 3. Key Upgrades in 2016. 4. Decoding the Design Chapters. And 5. Quality, Safety, and Survival. So, starting off with Section 1, the Steel Construction Rulebook, the foundation of the skyline. When an engineer successfully applies the rules in this book, they quite literally create a skyline. You see, this document is born out of past successful usage, rigorous research, and a really deep understanding of materials. Now, for a long time in engineering, there was this divide in how we calculated safety margins. You had allowable strength design, or ASD, on one side, and load and resistance factor design, or LRFD, on the other. What's so brilliant about AISC 360-16 is that it takes these two historically distinct design philosophies and just unifies them into one seamless, integrated standard. It gives engineers the flexibility to design according to either provision without needing 2 totally separate rulebooks, a real game changer. Moving right along to Section 2, Consensus and Continued Evolution, or the minds behind the mass. A standard like this doesn't just magically appear out of nowhere, right? The 2016 version supersedes the 2010 edition, and it reflects the continuous, relentless march of human knowledge and technological advancement in metallurgy and physics. But here's the coolest part. Behind all the dry math, the tables of symbols, and the steel shapes, there is a massive collaboration of diverse, brilliant human minds. This specification is an ANSI-approved consensus document. So it's not just a handful of academics sitting in a room. It's private practice engineers, building code officials, fabricators, and producers. They all bring their real-world experiences to the table to argue, deliberate, and finally agree on the safest, most efficient ways to build. They're all working together for public safety. Let's jump into Section 3, Key Upgrades in 2016. This is where we see engineering as a living science. The code is never static. It's always adapting as we learn from structural behaviors and test out new materials. Just take a look at these precise upgrades. The adoption of the ASTM F3125 umbrella bolt specification totally streamlined how we classify high-strength bolts. And the new ASTM specifications for hollow structural sections, or HSS, finally permit engineers to use a design thickness equal to the full nominal thickness of the member. That is a massive boost for efficiency. They also expanded structural integrity provisions for connections and added limit states for constrained access torsional buckling. These aren't just minor little edits, folks. These upgrades are the literal reasons we are safe sitting inside modern buildings today. And to highlight exactly how far we're pushing things, just look at this specific number, 80 KSI. The 2016 specification actually increased the limit on reinforcing bar strength to 80 kips per square inch for composite columns. This perfectly shows how engineers and metallurgists are constantly pushing material limits further and further, which is what allows us to build taller, lighter, and stronger structures than ever before. Okay, on to Section 4, Decoding the Design Chapters. Let's look at the anatomy of a building. So the specification organizes a building's skeleton incredibly logically by isolating the specific types of forces a piece of steel might face. First up in our rapid-fire chapter tour is Chapter D, covering tension. Just imagine this force as pulling a structural member apart like a giant rubber band. The rules in this chapter dictate exactly how much pulling force a steel shape can take before it yields or fractures. The code calculates the gross area of the steel and, critically, the effective net area, which accounts for any holes drilled into the steel for bolts, because, as you know, those naturally weaken it. That's instantly followed by compression in Chapter E. Think of compression as the force squishing columns down, kind of like stepping on a soda can under massive weight. Now, the challenge here isn't just the steel crushing, it's buckling. The specification provides rigorous math for flexural buckling, torsional buckling, and flexural torsional buckling. This ensures that tall, slender columns don't just spontaneously bow out sideways when they're carrying the immense weight of a skyscraper. Then we have flexure in Chapter F. This one is all about bending. It dictates how beams and girders distribute loads across a floor without snapping or deflecting way too much. When a load pushes down on the middle of a beam, the top of the beam compresses while the bottom pulls apart in tension. Chapter F balances these dual forces and sets the rules for preventing lateral torsional buckling, which is basically when a beam tries to twist out of the way of the load. And finally, we hit shear in Chapter G. Shear involves intense sliding and slicing forces primarily acting against the webs of those massive steel I shapes. Imagine holding a thick stack of paper and pushing the top away from you while holding the bottom. That sliding action, that's shear. Chapter G makes sure the web of the steel beam doesn't buckle or tear under those really intense slicing loads near the columns. Now, this macrostructure comparison clearly distinguishes the bones of our building, the structural members we just covered in Chapters D through I, from the joints or the connections, which are meticulously detailed in Chapters J and K. Because think about it, you can have the absolute strongest beams and columns in the world, but if the connections fail, the whole building falls. So, Chapter J provides the highly specific ingredients required to safely transfer those massive building loads from one member to the next. For welds, you've got very strict parameters for groove, fillet, and plug welds, which includes exact effective areas and filler metal requirements. And for bolts, it details high-strength applications and slip-critical connections, where the actual friction between the steel plates is just as important as the bolt itself. It's a highly precise recipe for structural integrity. Let's move to our final section, Section 5, Quality, Safety, and Survival. It's all about protecting the public. Designing the structure on paper is really only half the battle. Making sure it is actually built correctly in the real world is where Chapter N comes into play. It tracks the rigorous journey of steel from the shop straight to the sky, creating a multi-tiered safety net. Step 1 requires the fabricator to have stringent quality control procedures while cutting and welding the steel in the shop. Step 2 requires the erector to have their very own quality control while bolting it all together on site. And Step 3 mandates an independent quality assurance inspector to verify that everything matches the approved drawings and specifications. Independent verification happens at every single step of construction, no exceptions. But the standard even goes beyond everyday conditions. Appendices 4 and 5 are absolutely vital. Appendix 4 gives engineers the analytical tools to design steel structures to survive extreme, unpredictable events, like post-flashover compartment fires. This ensures the steel retains enough strength at elevated temperatures to allow everyone to evacuate. Meanwhile, Appendix 5 provides the rules for safely evaluating our aging existing structures through material testing and structural analysis, rather than just unnecessarily tearing them down. And that brings us to the end of our explainer. The code builds our future, for sure, but as we just saw with the evaluation of existing structures, it also fiercely protects our past. I want to leave you with this final provocative thought. The next time you look up at a towering steel skyline, or honestly, even just the roof of a local warehouse, ask yourself, what unseen rules, what invisible equations, and decades of consensus are quietly working together to keep that sky supported and protect your life today?